Sometimes it is hard to do everything at once. The Flight Management Computer, or FMC, is a tool you can use. It does many routine tasks and computations for you. The FMC reduces the work you need to do. The FMC stores information in internal files or databases. It has a navigation database and a performance database. The navigation database contains data from sources such as Standard Instrument Arrivals, or STARS, Standard Instrument Departures, or SIDs, and en route and approach charts. This data is kept current with frequent updates. All necessary airplane performance data is also stored in the FMC. The FMC receives data from airplane systems. It also receives data from the flight crew. The FMC uses information from the flight crew, airplane systems, and its own databases to calculate the optimum flight profile. It then sends commands to the autoflight systems. The FMC also sends data to the displays and the control display units, or CDUs. There are 2 CDUs, one for each pilot. The CDUs let you communicate with the FMC. You may put in and show FMC data with either CDU. The CDU has a display screen, alpha and numeric keys to put in data, function keys to show pages of data, and line select keys to select, put in, or remove data. Now let's look at the CDU display more closely. We'll start with the Performance Initialization page. Data lines are on the left and right side of the display. Data lines contain data that is put in automatically by the FMC or manually by the flight crew. Here are 3 examples of data lines. Line titles identify the type of data on the data line below. Some data lines contain boxes. You must put data in the boxes for the FMC to operate correctly. Some data lines contain dashes. It is optional to put data in a data line with dashes. You should put in the data if it is available to improve FMC operation. Some data lines already have data put in. The data has been put in by the FMC or by the pilot. Now let's look at how to use the CDU to put in data. Let's put in the cost index. You must put in the number 30. First, push the number 3 key. Notice that 3 shows at the bottom of the display. This area of the screen is the scratch pad. Your entry shows here first. Complete the entry. Push the 0 key. Make sure your scratch pad entry is correct. To move scratch pad data, you push the line select key adjacent to the applicable data line. To move 30, push the line select key adjacent to the cost index data line. That completes the cost index entry. If your scratch pad entry is not correct, you can use the clear key to clear the scratch pad. You push the clear key to remove the last character from the scratch pad. Push the clear key one time. If you hold the clear key, you can remove all the characters from the scratch pad. Hold the clear key. The FMC shows messages in the scratch pad. There are many scratch pad messages. In this example, the entry is invalid. When a scratch pad message shows, the message light illuminates. To remove a scratch pad message, push the clear key. You do not have to hold the clear key. Your entry stays in the scratch pad after the message clears. Push and hold the clear key to clear the scratch pad. The FMC will show a message in the scratch pad if there is an entry error or to tell you about system status. If a condition must be corrected before you continue FMC guided flight, the FMC shows a CDU scratch pad message and the FMC alert light on each pilot's panel illuminates. Clear the scratch pad message. Now let's continue to put in data. Let's put in the cruise altitude. You must use the correct format. Altitudes can be put in with these formats. To put in the cruise altitude, use one of these formats. You will learn more about data entry formats in other FMC lessons. The execute light is illuminated. Some data is not active or is not accepted by the FMC until you execute your entries. We'll discuss the execute key after you complete all performance initialization page data. Notice that the cruise wind line has a slash in the data line. The slash divides data on the data line. To put in cruise wind, you must use the slash key. Put 270/50 in the cruise wind line. You can also put in a piece of data in one side of the slash. The cruise wind direction has changed to 300. To change the wind direction entry, put in 300/. Now let's see how to put in negative values. Number entries are assumed to be positive unless a minus sign is used. Use the plus/minus key to put in negative values. You push the plus/minus key one time to show a minus. Put minus 47C in the top of climb OAT line. Enter the data as shown. You can put in temperatures in degrees Fahrenheit or Celsius. Your entry is in Celsius. The FMC calculates the equivalent Fahrenheit temperature. Now that the page is complete, you must execute the entries to make them active. To execute your entries, push the execute key. The word active is now in the title to show that the FMC uses the performance initialization page data. Modifications and the execute key are discussed more in other lessons. Next, we'll look at more CDU functions. Some lines have a caret symbol. When you push a line select key adjacent to a caret, the FMC will show a page or do a function. In this example, you can show the init ref index page. Push the line select key adjacent to index. From the init ref index page, you can show preflight and reference data pages. Select the position page. You put present position in this page for IRS alignment. You saw how to use the alpha and numeric keys to put data in the scratchpad. You can also make a copy of data on a data line. First, check to see that the scratchpad is empty. Next, push the line select key by the gate latitude and longitude coordinates. The coordinates show in the scratchpad. Next, move the data from the scratchpad to the set IRS position line. Many times, it is easier to make a copy of data than to put it in with the alphanumeric keys. You use the function keys to show pages. Push the LEGS key. The LEGS page shows the waypoints in the route of flight. Because one page cannot show all waypoints in this route, the FMC creates additional pages. This shows there are 3 pages of waypoints for this flight plan. This shows that you now see page 1. You use the next page key to move forward through the other pages. Push the next page key. The page number changed to show that this is page 2. To return to page 1, push the previous page key. Push the previous page key again. The last LEGS page shows. When there is more than one page, you can push the next page or previous page key to show any page. Next, let's look at data lines again. Small characters on a data line, like these, show values calculated by the FMC. Large characters show the data you have put in, or data that is part of a departure or arrival procedure you selected. Data can be deleted with the delete key. Tower tells you to remove this altitude constraint. First, check to see that the scratchpad is empty. Push the delete key. Notice that delete shows in the scratchpad. Push the line select key by the data that you want to remove. The large character constraint is removed. The FMC calculates a predicted value and shows it in small characters. The display shows that you have modified the route. Remember that some data is not active or accepted by the FMC until you execute your entries. Push the Execute key to complete the change. Not all data can be deleted. For example, the first waypoint on LEGS page 1 is called the active waypoint. If you try to delete the active waypoint, the FMC shows the invalid delete scratchpad message. Show the POS INIT page. Put the gate position in the Enter IRS position line. Show the route page. Clear the scratchpad message and put in the destination airport. I put in the remaining preflight data. Show LEGS page 3. Delete the altitude restriction at TAFTO and execute the modification. In this lesson, you will learn how to preflight the FMC. FMC Preflight lets other systems use FMC data. The preflight starts with the identification or IDENT page and continues in this sequence through the takeoff reference or takeoff ref page. The N1 limit page is used to select reduced climb thrust. After power-up, the FMC shows the IDENT page. Let's look at the IDENT page. First, make sure the airplane model and engine rating are correct. Next, check to see if the navigation database is correct. There are 2 navigation databases stored in the FMC. In this example, the active database can be used from October 31st to November 28th. And the inactive database can be used from November 29th to December 27th. The FMC uses the active database for its calculations. In this example, the current date is not within the active database dates. The FMC shows the scratchpad message nav data out of date. Clear the scratchpad. Next, change the navigation database. Make a copy of the inactive database date in the scratchpad, then put it in the active database line. You have changed the active database. The IDENT page preflight is complete. During the preflight, you use this line select key to move through the preflight pages. Next, show the Position Initialization or POS INIT page. The last position line shows the position the FMC calculated when power was removed at the end of the last flight. Put the departure airport in the reference airport line. The FMC shows the airport reference point coordinates from the navigation database. Next, put the gate identifier in the gate line. The FMC shows the coordinates for the gate. You should use the most accurate position available to align the IRSs. In this example, the gate position is the most accurate. Put the gate position in the Set IRS Position line. The IRS can now complete alignment. You can also put in the position manually. In this example, you do not know a gate identifier, but you know the latitude and longitude coordinates of your position. To put in the coordinates, include the latitude and longitude numbers, letters, and decimals. Do not put in spaces. Put the coordinates in the scratchpad, then put them in the Set IRS Position line. The POS INIT page is complete. Show the route page. The next step in the FMC Preflight is to put in the flight plan route. Route page entries are discussed in a different lesson. To save time, I'll put in the route for you. The route is loaded. show the Performance Initialization or PERF INIT page. You use the PERF INIT page to put in airplane and route data for performance calculations. Make sure fuel agrees with your fuel quantity indicators. You can put in the gross weight or the zero fuel weight. Use zero fuel weight for more accurate FMC performance calculations. To put in weights, divide the number by 1,000. Put in the zero fuel weight. The FMC calculates the gross weight. Put in reserve fuel. The FMC uses the cost index to calculate economy climb and cruise speeds. It is a number supplied by dispatch. The cost index adjusts the relationship between the cost of fuel and the other costs of airplane operation. In general, the higher the cost index, the faster the economy climb and cruise speeds. Put in the cost index. The FMC calculates a recommended minimum cost cruise altitude. Put in the cruise altitude from the dispatch data. After all data lines with boxes are complete, the execute light illuminates. The data is not active or used by the FMC until you push execute. You can put in the cruise wind and cruise altitude temperature data to improve the FMC predictions for your flight. The FMC uses this information to adjust your climb, cruise, and descent. Complete the remaining data lines. Put in the cruise wind. Put in the top of climb OAT. Execute. Active is in the title to show that the PERF INIT data is used by the FMC. The PERF INIT page pre-flight is complete. To continue the FMC pre-flight, push the N1 limit key. The FMC can calculate reduced takeoff thrust for the autothrottle. You select Reduced Takeoff Thrust on this page. A runway analysis or other approved airline performance data is necessary to calculate the reduced thrust takeoff or climb entry. For this example, the analysis is done. Reduced climb thrust selections show here. Climb 1 gives a climb limit reduced by 3% N1, or approximately 10% thrust. Climb 2 gives a climb limit reduced by 6% N1, or approximately 20% thrust. Select Climb 2. Next, show the Takeoff Ref page. The FMC calculates takeoff thrust for the engines. This is the thrust used by the autothrottle. Make sure that takeoff shows on the thrust mode display. Takeoff means full rated takeoff thrust will be used. Select the takeoff flap setting. The selected flap setting will allow the FMC to compute the V speeds based on the current gross weight. The FMC calculates V speeds for the takeoff. Enter the center of gravity CG. The CG will allow the FMC to compute the takeoff trim setting. Put in V1. Put in VR. Put in V2. These lines help you show pages that are not complete. In this example, the PERF INIT page is not complete. Use the line select key to show the PERF INIT page. The execute light is illuminated. All page data is complete, but the data is not active. Execute. Next, show the TAKEOFF REF page to see if the FMC Preflight is complete. The FMC Preflight is complete. We will discuss takeoff shift in a different lesson. You decide to do a reduced thrust takeoff and climb. Show TAKEOFF REF page 2. The FMC can calculate reduced takeoff thrust for the autothrottle. You select Reduced Takeoff Thrust on this page. A runway analysis or other approved airline performance data is necessary to calculate the reduced thrust takeoff or climb entry. For this example, the analysis is done. First, let's discuss the selected temperature or assumed temperature thrust reduction. These data lines on page 2 also show on N1 limit page 1 of 1. You normally put in the assumed temperature on page 1, but it can also be put in on page 2. Put the assumed temperature and the selected temperature line. If you put in an assumed temperature that is more than the outside air temperature by a large enough quantity, the FMC calculates a lower takeoff thrust limit for each engine. The FMC commands a reduced takeoff thrust to the autothrottle. The thrust mode display shows an assumed temperature reduced thrust takeoff of plus 35 degrees Celsius to show that reduced takeoff thrust is selected. The reference N1 bugs moves to the new takeoff values for the assumed temperature D rate. Next, delete the assumed temperature. The FMC commands full rated takeoff thrust to the autothrottle. There are 3 optional entries available on TAKEOFF REF page 2. Entry of these options refines the FMC performance management. Enter runway wind direction and speed here. Enter runway slope here. Valid entries for slope are U or plus for up and D or minus for downslopes, followed by the percent gradient. Runway conditions for dry, wet, or skid-resistant wet runways are entered here. Climb thrust reduction altitudes are entered here. Allowable entries are 800 feet to 9,999 feet. The engine out acceleration height can be set here. It displays acceleration height for flap retraction with an engine out. Allowable entries are from 400 feet to 9,999 feet. This area displays height for flap retraction. Allowable entries are 400 feet to 9,999 feet. The quiet climb system can be initialized after the initial FMCS setup is complete by turning the cutback feature line select key 6 right to on. The FMCS quiet climb system supports operations at airports with noise abatement requirements in effect. With the quiet climb system enabled, the FMC can provide automated operations by reducing and restoring thrust levels at pre-selected altitudes. By selecting Cutback On, the cutback N1 limit is computed to provide a minimum thrust cutback for a climb gradient of 1.2%. The thrust reduction altitude entered in line select key 5 left is the altitude at which cutback will occur. The restore altitude entered in line select key 5 right is the altitude at which climb thrust will be restored. You use the initialization reference key or init ref key to go back to the initialization and reference pages. For example, you want to see the POS INIT page again. First, push the init ref key. One of the initialization or reference pages shows. A different page shows during different parts of flight. Next, push the line select key adjacent to index. If you select the index prompt, the init ref index always shows. The init ref index lets you show any of the initialization and reference pages. Now, show the POS INIT page. Use the dispatch data to do the FMC Preflight. First, complete the IDENT page. Continue the Preflight. Show the POS INIT page. Use the most accurate position to align the IRSs. Continue the Preflight. I put in the route for you. You will learn how to put in the route in a different lesson. Continue the Preflight. Complete the PERF INIT page. Show the N1 limit page. Select Reduced Climb Thrust. Show the TAKEOFF REF page. Complete the TAKEOFF REF page. Enter the data as shown and push the correct key. Put in V1. Put in VR. Put in V2. These are the CDU pages used for FMC Preflight. This lesson shows how to put in the route on the route page. Most routes require a departure procedure for takeoff. You select departure procedures and transitions on the departures page to make them part of the flight plan. Let's continue the Preflight from the POS INIT page. The POS INIT page Preflight is complete. Notice that Boeing field has been put in. Show the route page. The message light illuminates because KBFI is in the scratch pad. The FMC copied KBFI from the POS INIT page to the route page. This can save time while you start to put in the route. You will manually put in this route from Boeing Field to Los Angeles. Start with the departure airport. Put the ICAO identifier, KBFI, in the origin line. Put in the ICAO identifier for Los Angeles, KLAX, as the destination. The company route is used to put in company-defined routes. This is discussed later. Put in the flight number. Put in the runway. Page 1 is complete. Display page 2 to enter the routing. Each route segment is put in ATC format, almost the same as regular flight plan entries. The route segment or airway information is put in on the left, and the endpoint of the route segment is put in on the right. Put in Seattle as the first endpoint under the To column. Direct is automatically put in the Via column if a route segment is not put in. Next, put the high altitude airway, J1, in the subsequent Via line. There are many waypoints along J1, but only the endpoint of your route segment must be put in. To complete the segment, put Avenal in the box prompts under the To column. Continue to put in the route in the order shown. The route is in, but it is not active. An inactive route is shown in cyan. You must activate the route before the autoflight system can fly it. There are 2 steps to make a route active. First, select the line select key adjacent to activate. The execute light illuminates. Second, push the execute key to make the route active. The route page title changes to active. The route becomes magenta, and after airborne, the autopilot can fly the active route. You can also use the company route line to put in the flight plan. A company route is a predefined route that your company loads into the navigation database. The entire route is put in with the company route identifier. Put in the company route identifier. The company route includes most of the route data you put in before. Company routes can include the runway and SID, but the runway and SID are often left out because of potential runway changes. Your flight contains a departure procedure and a transition. The departure arrival key shows the departure arrival index page. From this page, there is a prompt to get access to the departures page for the origin airport. To go back to the departure arrival index page, you can push either the index prompt or the departure arrival key. From here, you can show the arrivals for the origin or the destination airport. Show the departure arrival index page. The arrival prompts are used to show the arrivals page for the origin or destination airports. The prompts are discussed in a different lesson. Departures or arrivals for other airports show after you put in the airport ICAO identifier in these lines. Show the KBFI departures page. You use the departures page to select the departure runway, departure procedure, and transition for the route origin airport. Active shows by the departure runway because you put a runway in the route page. Active shows that the runway is part of the active route. Select the departure procedure for your flight. This shows that the departure procedure is selected. The execute light illuminates. This shows a route modification is in progress. Modifications show as white dashes. On route page 1, Mod shows in the page title. An erase prompt comes into view. The prompt erases all modifications and shows the original active route. Use the erase prompt to erase the modifications. The route modifications are erased, the original active route shows, and the execute light extinguishes. Select the departure procedure again. These are transitions available for the selected departure procedure. You can select Hump, Orton, or VAMPS. Select the correct transition for your route. The departure entries are complete, but the map shows that the modified flight plan discontinues after Orton. Go back to the route page to connect the discontinuity. Show route page 2. The Laker 3 departure Orton transition is shown. A route discontinuity follows the SID. A discontinuity occurs when two route segments are not connected. As you can see, the rest of the route is the same as before. ATC clears you from the departure transition at Orton direct to Alder. Alder is on J1. You must connect Orton to Alder to make the route the same as the clearance. Put Alder in the boxes to connect the discontinuity. Execute the modification. The route entry part of the preflight is complete. Put in the route as shown. Enter the data as shown. Make the route active. Next, select the departure. Show the route page.
Show route page 2.
Remove the discontinuity and make the route the same as the clearance. Execute the modification. The route page looks almost the same as a flight plan. It shows route segments such as departures,
direct routing, and airways.
More detailed data is found on other pages. Expanded route data is on the route legs page. The legs page looks almost the same as a paper flight log. Each waypoint along the route is shown. The legs page also shows leg direction, leg length, waypoint speed, and waypoint altitude. On a route data page, you see waypoint ETA and wind. The legs page. When you push the legs key, legs page 1 is always shown. Show the route data page. A route data page is available for each related legs page. Push the next page key to show route data page 2. Push the legs prompt to go back to legs page 2.
The active waypoint shows in magenta on legs page 1.
Above the name of each waypoint is the magnetic heading or the magnetic course to that waypoint. True courses are usually necessary at high latitudes. The letter T shows a true course. Laker is a set waypoint. Its geographic position does not change. The location of some waypoints is not set. Flight conditions that include wind, true airspeed, thrust available, and airplane pitch change their location. These are conditional waypoints. Conditional waypoint names are shown in parentheses. In this example, the 312-degree heading is held until the airplane is at or above 420 feet. If conditions change, the location of the waypoint changes. This conditional waypoint is an altitude constraint. Other constraints could be VOR radials, DMEs, or intercepts. Conditional waypoints can only be put in the flight plan as part of a SID, STAR, or an approach procedure. They cannot be put in manually. Distances are shown in the center column. For the active leg, the FMC shows the calculated distance from the airplane to the active waypoint. For all other legs, the FMC shows the calculated distance between waypoints. The speed at each waypoint is shown. The altitude to cross each waypoint is also shown. Small characters are FMC estimated values. Large characters are constraints. Constraints can be put in by you or by the FMC as part of a procedure. How do you put in speed or altitude constraints? Speed constraints must be followed by a slash. Put in the speed constraint. Execute. There are 4 types of altitude constraints. At altitude constraints have no letters. At or above altitude constraints are identified by the letter A. At or below altitude constraints are identified by the letter B. Altitude restrictions between 2 altitudes use an A with the lower altitude and a B with the higher altitude. These restrictions can only come from the FMC database. They cannot be put in manually. Put in the altitude constraint. The slash is optional for altitude constraints. Enter the data as shown. Execute. Put in the speed and altitude constraint at Orton. The 2 constraints can be put in at the same time. Enter the data as shown and push the correct key. Execute. To delete altitude and airspeed constraints, push the Delete key and select the waypoint constraints to be deleted. Delete the airspeed and altitude constraints at Orton. Execute. Next, we will discuss how the FMC helps the flight crew schedule, monitor, and change the airplane's vertical performance with vertical navigation, or VNAV. The FMC schedules a vertical climb path for the flight from the origin airport to cruise altitude. The path is calculated for the gross weight, selected thrust, forecast winds and temperature, waypoint altitude or airspeed constraints, airspeed restriction altitude, the selected climb mode, and the cruise altitude. During cruise, the FMC schedules an economical speed and step climbs. The FMC also schedules a vertical descent profile calculated for idle engine thrust, estimated winds and temperatures, and deceleration at the speed restriction altitude. The FMC changes the descent profile for altitude or airspeed constraints and the approach. The FMC has 3 VNAV-related pages: the climb page, the cruise page, and the descent page. Let's look at the climb page. You use the Climb page to monitor and change the climb profile. The title of the Climb page shows the active climb mode. In ECON Climb, the FMC supplies the most economical climb profile calculated from the cost index. Push the line select key adjacent to max rate and execute the modification. Max rate climb gives the least time to climb to altitude. Push the line select key adjacent to max angle and execute the modification. Max angle climb gives least horizontal distance to climb to altitude. Change to ECON Climb. If there is a waypoint with an altitude constraint, the FMC shows it here. The constraint data comes from the LEGS page. You can delete the constraint on the Climb page or the LEGS page. Use the Climb page to delete the constraint. Execute the modification. When you delete the altitude constraint, the LEGS page also shows the deletion. If you put a constraint on the LEGS page, the Climb page also shows the new constraint. Use the LEGS page to put in a constraint of 15,000 or above at Orton.
Enter the data as shown. Enter the data as shown and push the correct. Enter the data.
Execute the modification. The FMC shows the time that you will cross the constraint waypoint and the distance to the constraint waypoint. The scratchpad message Unable Next Altitude shows if you will be below the constraint altitude at the waypoint. The Climb page shows how low you will be. Clear the scratchpad message. The FMC shows the target airspeed and Mach for the climb and the speed restriction if there is one. The FMC calculates and shows the target airspeed and Mach number for the related climb mode. The speed restriction can be a waypoint-related constraint or a value from the airport database for the origin airport. If a restriction is not available, the FMC uses 250 knots below 10,000 feet as a default. The FMC highlights the active airspeed. In this example, you are below the speed restriction altitude of 10,000 feet. The active airspeed is 250 knots. Put in a new airspeed restriction of 240 knots below 15,000 feet.
Enter the data as shown and push the correct key.
Execute the modification. Delete the speed restriction. Execute the modification. When there is no airspeed restriction, the active airspeed is the target airspeed related to the active climb mode. If you put in a different airspeed, then the FMC uses the new airspeed value for the climb. Put in a target climb speed of 260 knots.
Enter the data as shown.
Execute the modification. When you put in a climb target speed, the title of the climb page changes to show the new speed. The airplane climbs at 260 knots. You can also change the cruise altitude on the climb page. Put in a new cruise altitude, flight level 350. Execute the modification. The FMC shows the new cruise altitude on all pages that show cruise altitude. You receive this clearance. Modify the climb page.
Enter the data as shown and
The FMC commands a 260 knot speed restriction until 15,000 feet and continues the climb to flight level 350. Put in the new altitude constraint. Use the legs page to put in the altitude constraint. You cannot cross Orton at or above 10,000 feet at this rate of climb. Change to max angle climb rate. Push the line select key adjacent to max angle. You have made the altitude constraint. Resume normal climb. If the climb page is shown during your climb, the display automatically changes to the cruise page at cruise altitude. During cruise flight, the cruise page is the active VNAV page. The title shows the active cruise mode and the current cruise altitude, the same as the climb page. The FMC calculates and shows the optimum cruise altitude for maximum economy and the maximum altitude. To change to a lower cruise altitude before the top of descent, put the new cruise altitude in the cruise page. To do this, you can manually put in the new altitude in the scratch pad. But an easier procedure is to set the new altitude on the MCP and have it automatically put in the scratch pad for you. The scratch pad shows MCP altitude changes only when the cruise page is in view. Put in the new cruise altitude. Execute the modification. The display changes to the cruise descent page. The FMC does a 1,000 feet per minute descent at cruise airspeed. We will discuss descents in another lesson. Put in the new cruise altitude. Execute the modification. The display changes to the cruise climb page. The FMC does a climb at cruise airspeed and climb thrust. During cruise, the FMC defaults to economy speed. Put in Mach 0.7 cruise speed. Execute the modification. Change to economy speed again. Execute the modification. Long-range cruise gives maximum range or minimum fuel use. If you are more than 100 miles from top of descent, the FMC shows the Step 2 altitude line. The Step 2 altitude line helps you examine step climbs for better economy. Put flight level 390 in the Step 2 altitude line. Below the Step 2 altitude, the FMC shows the time and distance to the first possible step climb point. The FMC calculates that you are past this point and shows now. Normally, the FMC shows the wind here. When you put in a step climb, you can also put in new wind. The wind at flight level 390 is 250 at 60 knots. The actual wind data line header changes to estimated wind to show that you put in the wind. The step climb data is information only. It is not part of the flight plan. This is the fuel remaining at Los Angeles and savings if you do the step climb. This step climb gives better fuel economy. Put the step climb altitude in the cruise altitude line and execute. Use the Step 2 altitude line to find out when you can climb to flight level 410. When can you climb to flight level 390? The wind at flight level 390 is 160 at 36. Put the new wind in the cruise page to make FMC predictions accurate. You are at the step climb point. Use the cruise page to climb to the new cruise altitude. The FMC does a climb at cruise airspeed and climb thrust. Use the cruise page to descend to the new cruise altitude. Slow to the new airspeed. Change to economy speed. Are two types of VNAV descents, path and speed. Each descent is flown differently, but the FMC uses the same descent profile with a speed or path descent. In a VNAV path descent, the autothrottle first retards and then holds idle arm, but can command FMC speed mode if ground speed becomes too low to maintain FMC vertical path. The AFDS holds FMC target speed. The pilot monitors and adjusts the speed if necessary. In a VNAV speed descent, the autothrottle first retards and then holds idle arm. The AFDS holds FMC target speed. The pilot monitors and adjusts the descent, if necessary, to stay on the desired descent profile. Let's see how the descent profile is calculated. The FMC starts with the end of descent point. The FMC then calculates a path for approach speed reductions and flap extensions. Before the approach, the FMC assumes descent with idle thrust, flaps and gear up, and speed breakdown. The FMC makes a top of descent point where the descent profile and cruise altitude come together. The FMC adjusts the descent profile for speed reduction at the airport speed restriction altitude. This moves the top of descent back and shortens the cruise phase. The FMC adjusts the descent profile for waypoint speed or altitude constraints. This moves the top of descent back and shortens the cruise phase again. Winds and temperatures also change the descent profile. When you put in forecast winds, the FMC adjusts the top of descent. The FMC uses all of these to calculate the top of descent point. The result is the most economical descent for the route and weather. The end of descent is near the destination airport or near the destination runway. If you do not put in an approach, the FMC assumes a straight line between the last waypoint on the flight plan and reference airport or runway. If you select an arrival or approach, the end of descent point is the last waypoint in the descent with an altitude constraint. You are 50 miles from top of descent. Show the descent page. Show the descent forecast page. You put in forecast ISA deviation, QNH, and winds for up to 3 altitudes on this page. Put in the ISA deviation and QNH. Enter the data as shown. Enter the data. Enter the data. You can put in up to 3 winds in any sequence. Put in the wind for flight level 210. For this example, put the wind on the first wind line. Continue. Put in the wind for 15,000 feet. For this example, put the wind on the second wind line. Continue. Execute the modification. Show the cruise page. The distance to the top of descent changes. A path descent is the most economical descent. During a path descent, the FMC controls pitch to stay on the path. You possibly have to use thrust or the speed brake to keep the airspeed you want. 5 miles from top of descent, the FMC scratchpad message Reset MCP Altitude shows. Reset the MCP altitude. The FMC automatically commands a descent when you pass the top of descent point. The descent page shows automatically. The FMC commands idle thrust. The pitch mode stays VNAV path, and the FMC controls pitch to stay on the path. The speed restriction line shows the airport speed restriction for your destination. You can put in a different speed and altitude restriction. Green circles on the navigation display map mode show where the deceleration segment starts and stops. When you are near the airport speed restriction altitude, the descent path angle decreases. The FMC commands higher pitch and the airplane slows. As speed decreases below the speed restriction, the FMC commands lower pitch to descend below the airport speed restriction altitude. The FMC commands a speed 10 knots lower than the airport speed restriction. In this example, the airport speed restriction is 250 knots below 10,000 feet. The FMC commands 240 knots. This gives a buffer for small airspeed changes. Information about the next waypoint with an altitude constraint shows here. If there is a waypoint with an altitude constraint, the path will come to the altitude at the waypoint. After the waypoint, a new path is calculated to the next constraint waypoint. The airplane now descends on the new path to the next calculated constraint waypoint. When you are close to the destination airport, the FMC commands flaps up maneuvering speed. Set flaps 1. When you extend flaps, the FMC commands speeds for the flap positions and your weight. If you do an ILS approach, VNAV disconnects at glide slope capture and the MCP speed display opens. Next, we will do the same descent using speed descent mode. You are level at cruise, near top of descent. Show the descent page. The FMC defaults to a path descent. If a speed descent is necessary, you usually have to select it. But if there is no altitude constraint at a waypoint in the descent, a path descent is not available. In this example, a path descent is available. Push the line select key adjacent to speed. Execute the modification. The speed descent page shows. Although the speed and path descent pages look mostly the same, the descents are very different. Recall that a path descent is the most economical descent. A speed descent is more flexible than a path descent. During a speed descent, the FMC controls pitch to stay at a target airspeed. The FMC does not try to stay on the path. Thus, a speed descent is less economical. You will possibly have to use the speed brake or thrust to stay on the path you want. You can stay on the VNAV path or a different path. Reset the MCP altitude for descent. In this example, with no altitude constraints, the FMC automatically commands a speed descent when you pass the top of descent. The FMC commands idle thrust. The pitch mode changes to VNAV speed. And the FMC controls pitch to stay at the target airspeed. Remember, you are responsible to stay on the path. When you are near the airport speed restriction altitude, the FMC commands higher pitch and the airplane slows. The pitch mode temporarily changes to VNAV path as the FMC controls pitch to stay on a path above the airport speed restriction altitude. In this example, the airplane is below the VNAV path. The FMC does not try to go back to the path. As speed decreases below the speed restriction, the FMC commands lower pitch to descend below the airport speed restriction altitude. There is a second waypoint with an altitude constraint. Recall that in a path descent, the FMC calculates a new path to the second waypoint. During a speed descent, the FMC will make sure you make the altitude constraint. Then the airplane will continue to descend to the next altitude constraint. At the altitude constraint, the FMC commands level flight until you pass the waypoint. The FMC temporarily increases thrust to keep the target speed. The pitch mode temporarily changes to VNAV path. The FMC commands slower speeds for the approach and flap extensions, the same as a path descent. If you do an ILS approach, VNAV disconnects at glide slope capture and the MCP speed display opens. ATC asks you to descend before the FMC calculated top of descent point. Reset the MCP altitude. Show the descent page. A path descent is planned. Push the line select key adjacent to descend now. Execute the modification. The FMC commands a 1,000 feet per minute descent. Until you come to the VNAV descent path. Then the FMC commands idle thrust and pitch to follow the path. Next, let's do an early descent using VNAV speed. I reset the MCP. Before you do the early descent, change to a speed descent. Start the early descent. Execute the modification. The FMC commands an idle thrust descent at the target airspeed. The FMC does not try to go to the VNAV path. If you put in accurate descent forecast data, the vertical deviation is usually near zero and the airspeed is near the target. The wind can be different than the forecast wind you put in the FMC. In this example, the tailwind is more than the wind you put in the FMC. During a path descent, the FMC commands pitch to keep the path. But the airspeed will be higher than the target. You can use the speed brake to add drag and decrease airspeed to the target. If you let speed increase to 10 knots or more than the target, the FMC shows the scratchpad message, drag required. You are below the airport speed restriction altitude. If you do not use the speed brake when the drag required message shows VNAV disconnects when the airspeed is more than 5 knots above the airport speed restriction. The FMC shows the scratch pad message, overspeed disconnect. Let's look at the same conditions for a VNAV speed descent. During a VNAV speed descent, the FMC commands pitch to keep the target airspeed. The tailwind moves the airplane above the VNAV path. Use the speed brake if you want to go back to the VNAV path. In this example, you are near a waypoint with an altitude constraint during a VNAV speed descent. If you let the airplane go above the VNAV path, the FMC shows the scratch pad message, unable next altitude. You cannot make the altitude constraint at this rate of descent. In the next example, the headwind is more than the wind you put in the FMC. During a path descent, the FMC commands pitch to keep the path. But the airspeed will be lower than the target. You can use the thrust to increase airspeed to the target. If airspeed decreases to 10 knots or more below the target, the FMC commands more thrust to increase airspeed to the target. During a VNAV speed descent, the FMC commands pitch to keep the target airspeed. The headwind moves the airplane below the VNAV path. Use thrust if you want to go back to the VNAV path. The FMC calculates a new descent path and top of descent when you do a modification. Put in all known descent and approach data before you start descent. For example, if you change the target speed on the descent page, the FMC calculates a new VNAV path. A slower descent speed moves the top of descent closer to you. You are on the path. Put in the new descent speed. Enter the data as shown. Enter the data as the FMC calculates a modified path. Execute the modification. When you execute, the vertical deviation changes suddenly. You are on the path again. Resume normal speed by selecting the ECON prompt. The path changes again. The waypoint restriction line shows the next waypoint with an altitude constraint. You can delete an altitude constraint here or on the legs page. Use the descent page to delete the constraint at Dene. The FMC calculates a new path. VNAV path and VNAV speed descents do path corrections very differently. If you are below the path in a path descent, the FMC commands less pitch to decrease the descent rate. The FMC commands more thrust to keep the target speed. You are above the path in a path descent. The FMC pitches down to get back to the path. And the airspeed increases. When this occurs, the airspeed can go to VMO. Use the speed brake to decrease airspeed. In a speed descent, the FMC does not try to stay on the path. If you want, use the speed brake or thrust to stay on the path. But if you are below the path and there is a waypoint with an altitude constraint, the FMC commands level flight at the constraint altitude. The descent continues after you pass the waypoint. You are not at top of descent. Start a VNAV path descent now. The tailwind is more than forecast. Do the applicable procedure. Use VNAV to change the descent speed. Use the descent page to delete the altitude constraint at Ephrata. Show the descent forecast page. Put in the ISA deviation and QNH. Put the descent wind on the first wind line. Complete the change. Set the FMC for a VNAV speed descent. Reset the MCP for descent. Correct to the VNAV path. In this lesson, you will see how to put in an arrival and an approach into the FMC. You will see the approach reference page. You will see how to put in a diversion airport and route. You will see how to put in a visual approach into the FMC and then link it to the diversion route. Flight 678 is ready to prepare for descent and arrival into Los Angeles. ATC provides your clearance. Use the Arrivals page to put this into the FMC. First, show the Departure Arrival Index page. Next, show the Arrivals page for the destination airport. Stars are shown on the left. Approaches are shown on the right. If more than 5 stars or approaches exist, more pages are available. Show KLAX Arrivals page 2. Select the star. Only the selected star is shown. All other stars are removed. All transitions related to the selected star are now listed. These transitions are used to connect the route to the star. Select the transition. Select the approach on the next page. Like the selected star, only the selected approach is shown. The approach includes missed approach routing and holding if the missed approach procedure is part of the published approach.
Approach transitions that apply to the selected approach are shown. These transitions include the initial approach fix, feeder fixes, and fixes that provide routing to the initial approach fix.
Select the approach transition. The star and its transition, the approach and its transition have been entered. However, these entries often create route discontinuities. Show the LEGS page to check for route discontinuities. LEGS page 1 is complete. Check the remaining pages. Connect the discontinuity. The discontinuity has been connected. The flight plan is continuous. Make the modifications active. Show the Arrivals page to see the change. All stars and approaches for the destination airport are shown in their initial order. This lets you choose any star or approach if your clearance changes. Select the next page. The active star and approach are shown. Star and approach have been put in. Now you will see how to use the approach reference page.
In flight, the approach reference page is shown when you push the INIT ref key.
Show the approach reference page. The gross weight line shows the FMC computed gross weight or crew input weight. If you try to put in a gross weight that is not in the allowed range, invalid entry is shown in the scratch pad. Each of the 3 VREF speeds are based on a landing flap setting and the gross weight. Entry of VREF and wind correction is discussed in another lesson.
Information for the selected approach is shown. This information includes runway length, the frequency and the identifier,
and the front course of the selected approach. After the missed approach due to the earthquake at Los Angeles, all runways are closed.
A diversion airport needs to be put into the FMC. Based on data you have available, the best diversion airport is Fresno Air Terminal, KFAT. Show the route page. Display route page 1. Put in the diversion airport Fresno, KFAT, into the destination line. Show route page 2 of 2.
Put in the expected routing after the missed approach holding. You can see the missed approach routing is still in the FMC. Show the legs page to see what remains of the missed approach procedure. Line 1 confirms the holding pattern will be active after you execute. Therefore, the airplane will not leave the holding pattern. This is good, since you do not have clearance yet to leave holding. Make the modifications active. ATC needs to know what cruise altitude you want for diversion.
Show the PERF INIT page. The PERF INIT page shows the optimum trip altitude.
Based on your request, ATC has transmitted your expected clearance altitude.
The clearance altitude may be put in on the PERF INIT page, the climb page, or the cruise page.
Put in the cruise altitude. Make the modification active. Weather is VMC at Fresno. Here is your approach clearance. Show the Fresno Arrivals page. The visual approaches are shown after the header runways. Select the expected approach. An entry into the runway extension line creates a waypoint on final at a distance you specify. Put in the runway extension to create the waypoint on final. Check the legs page for discontinuities. A discontinuity exists between Avenal and the waypoint on final. Connect the first discontinuity. Another discontinuity exists between the waypoint on final and the runway. Connect the discontinuity. Make the modifications active. This lesson shows how holding patterns are done with the FMC. You will see how to change the data on the hold page. The FMC can make a holding pattern at the airplane's present position. The FMC can make a holding pattern at a waypoint. You will also see how to exit a holding pattern. Push the hold key to show the hold page. The hold at line is on the legs page. It shows when the active route does not contain a holding pattern. Select the present position prompt to hold at your present position. The hold page shows data for a standard holding pattern along your route. The holding fix shows as a present position waypoint. The airplane turns to start holding immediately after you execute. execute the modification. The initial turn into holding is shown. It uses the airplane's current ground speed. The airplane starts to slow to the target speed. You can put in a holding pattern at a fix that is not in the active route. The holding fix and pattern can be put into the route at the same time. Push the hold key. Put Avenol into the Hold At boxes. The message Hold At Avenol shows in the scratch pad. This is because Avenol is not a waypoint in the active route. The route shown on the legs page must be modified. The FMC will put Avenol and the holding pattern where you select. Select line 2 to put in the waypoint and holding pattern. The hold page shows data for a standard pattern on the course from CZQ-05. The FMC uses the flight plan course when there is no published holding pattern. Your clearance is to hold on the 304-degree radial. Put the 124-degree course into the inbound course line. Execute. The holding pattern dimension is small to prevent clutter. The holding pattern dimension becomes normal when the airplane is 3 minutes away from the holding fix. Show the legs page. The FMC put in Avenol as a waypoint on the line you selected, and the holding pattern was put in on the next line. The FMC put a discontinuity in the route after holding. You are inbound to the holding fix. Show the hold page again. The hold page shows the best speed for holding. The FMC calculates it from the airplane's altitude, gross weight, and flap position. The best speed is moved by the FMC to the target speed line. VNAV uses this speed as holding speed. The flight crew must verify that the speed obeys the ATC holding rules. Holding speed can be changed on the legs page or on the hold page. Put in 240 knots for the target speed. Execute. VNAV starts to decrease airspeed at approximately 3 minutes before the fix, and the holding pattern becomes normal size. The holding pattern page becomes active when you arrive at the fix. LNAV calculates the type of pattern entry from the difference between the inbound course and the airplane's heading when you pass the fix. Since the airplane is not required to fly directly over the holding fix during initial entry or exit, the FMC will calculate either a flyover or fly-by-hold entry and exit track, depending on path geometry. This supports increased R&P capability by ensuring that the airplane remains on the maneuvering side of the holding pattern and within the depicted racetrack pattern even during a parallel entry. The FMC changes the bank angle based on true airspeed and wind. The maximum is 30 degrees of bank. The arrival procedure into Los Angeles has been put in for you. The discontinuity after Avenal has been connected. Select the Exit Hold prompt. After the Execute key is pushed, the prompt changes to Exit Armed, and the LNAV route changes to a direct course to the holding fix. Execute. The airplane turns immediately to the inbound leg, but stays at holding airspeed and altitude. At Avenal, the airplane exits holding and accelerates to cruise airspeed. You are in the descent to KLAX and are given a new clearance. SADI is the active waypoint. Show the hold page. Select the next hold prompt. Put the new holding fix into the boxes. Verify that the turn direction and inbound course are correct. Put in the speed. Execute. Show the legs page to put in the clearance. Delete the holding pattern at SADI. Connect the discontinuity. Execute. You are in a descent to flight level 250. Put in the holding pattern at raise. The missed approach holding pattern is shown because it is already in the active route. Select the next hold prompt to put in a different hold. Put raise into the hold at boxes. Since raise was a route waypoint, the FMC put the holding pattern into the legs page with the flight plan course to the fix. There is not a route discontinuity. Put L into the turn direction line. Enter the data. The FMC puts in a leg time calculated from your altitude. Put 10 into the leg distance line. Leg distance overrides the leg time. The pattern dimension is not adjusted until the hold page becomes active. Make sure that the target speed is correct. Execute. The page number is the same as the total number of holding patterns in the route. The missed approach holding at RAFs is on hold page 2. Push the next page key to see the missed approach holding pattern. The hold page 2 of 2 is shown. Use the next page or previous page keys to see the holding patterns in the FMC flight plan. Use the next hold prompt to make new holding patterns. Show hold page 1. You are now holding at raise. This line shows the ETA for the holding fix. ETAs at subsequent waypoints are calculated from this value until an expect further clearance time is put in. Put in the EFC time. ETAs and fuel predictions at subsequent waypoints are now calculated with the EFC time. This line shows how much time is available to hold. The time is calculated from the fuel remaining after you subtract reserves and en route fuel to the destination. The FMC calculates you will burn some of your reserve fuel. This calculation uses holding until the EFC time, then a descent and landing at KLAX. The new EFC has been put in for you. Flight 678, hold at present position. Hold at present position. Execute the modification. Flight 678. Expect further clearance at 1725. The EFC time will decrease the necessary reserves. Flight 678, your revised further clearance time is 1705. You are cleared direct to ELN. Execute the modification. Hold at ELN. Execute the modification. Make the holding course 268 degrees. Execute the modification. Change holding airspeed to 230 knots. Execute the modification. Exit the holding pattern. Execute the modification. The FMC uses VOR and IRS data to calculate its position as before. The new 737 also has GPS. When GPS signals are available, the FMC uses GPS data as primary. GPS data is more accurate than radio or IRS data. If you are in the air and GPS data is not available or not accurate, the FMC will use radio data as primary. The FMC does not use radio position data on the ground, but it does use GPS position data. This gives accurate FMC position during extended ground operations. GPS time is very accurate. It shows on the POS INIT page. The position of each GPS receiver shows on the POS REF and POS shift pages. Show the nav options page. You can stop FMC use of GPS updates with the GPS update prompt. Stop GPS updates. GPS position data is re-enabled after landing before the next flight. First, the FMC uses GPS data to calculate its position in flight. Then the FMC uses distance data from 2 DME stations to calculate its position. The FMC continuously tunes different DME pairs to recalculate its position. Show the POS INIT page. Show the next page. The POS REF page shows each IRS calculated position, the GPS position, and the position that the navigation radios give. The FMC uses input from one or more of these systems to calculate its position. In this example, the FMC uses GPS data. Show the next page. Use the POS shift page to check radio, GPS, and IRS position data, or to shift the FMC position. Position data on the POS shift page is shown in relation to the current calculated FMC position. You can shift the calculated FMC position to one of the other positions shown. Select the left IRS position. Execute. The FMC position shifts to the left IRS position. The FMC uses the left IRS position until you select a different position. With GPS update off, there can be a map position error when you are at the departure runway. During takeoff, when you push a toga switch, the FMC automatically changes the map position to the departure end of the runway. This makes sure that the flight starts with an accurate FMC position. If you depart from a runway intersection, you can change the takeoff shift line on the TAKEOFF REF page. You are at intersection B2. Put in the runway intersection data. When you push a toga switch, the FMC position moves to the intersection you put in. The progress key.
Progress page 1 of 4 shows your progress along the FMC route. It shows all data necessary to make a position report. Now show progress page 2. Progress page 2 displays wind, track, path, temperature, and speed data.
Touch part of the progress page to see data about it. Touch the arrow to continue.
Now let's look at progress page 3. The RTA progress page initiates the required time of arrival, or RTA mode, provides advisory data on flight progress in the RTA mode, and advises control times such as recommended takeoff time to meet RTA. Touch part of the progress page to see data about it. Touch the arrow to continue. Now show progress page 4. The RNP progress page displays essential required navigation performance, or RNP, and ANP, or actual navigation performance information. Page 4 shows the waypoint identifier, lateral and vertical RNP and ANP values, course, distance, glide path, cross-track error, speeds, altitudes, and vertical deviation. Touch part of the progress page to see data about it. Touch the arrow to continue.
Next, let's look at the Fix Information page. Push the Fix key. The Fix Information page lets you show data in relation to a fix on the navigation display map mode. The fix data is information only. It is not part of the FMC route.
There are 6 Fix Information pages. You can put a different fix in each page.
You can put in any fix that is in the navigation database. Put the waypoint lengths in the boxes. Lengths shows on the map as a green fix. Next, select the Abeam prompt. The map shows a radial from lengths where the route passes Abeam lengths. ETA, distance, and altitude for the Abeam point show on the Fix Information page. You can put data in these radial distance entry prompts to show a radial from the fix or distance circle around the fix.
You can put in a radial, a distance, or both. First, enter the radial only at line select key 2 left. If you put in a distance, you must use the slash key. Put in the distance only at line select key 3 left. Lastly, put in the radial and distance at line select key 4 left.
To remove the fixed data from the map, use the Delete key. Delete lengths. You are at intersection B3 for an intersection departure. Put in the FMC Position update data. You are cleared for takeoff. Touch the correct control to update the FMC position. Use the progress page to find ETA and fuel remaining for your destination airport. What is the current SAT? Use the Fix Information page to show when you will be Abeam click. Remove the fixed data from the display. Air traffic controllers frequently make many changes to your route of flight. With the FMC, you can easily change your flight plan route. Your route contains many waypoints. Here is an example of some changes you can do. Use the LEGS page to add, delete, and change the sequence of waypoints in your flight. To obey this clearance, you must delete Red Bluff from the route. Use the delete key to delete Red Bluff. Execute the modification. All waypoints except the active waypoint can be deleted with the delete key. A route discontinuity shows where the waypoint was deleted. A route discontinuity is two route segments that are not connected. Until the discontinuity is connected, there is no FMC course guidance after Rogue Valley, and the airplane continues on the same course it needed to get to Rogue Valley. Oakland is the desired waypoint after Rogue Valley. Thus, to obey the clearance and connect the discontinuity, put Oakland after Rogue Valley. Execute the modification. The discontinuity is now connected and course guidance is given after Rogue Valley. All of the waypoints below Oakland move up in the list. With this clearance, Red Bluff is the necessary waypoint after Rogue Valley. Put RBL on the line after OED. A route discontinuity also shows when a waypoint is added. This time, let's connect the discontinuity before you execute the modification. Oakland is the necessary waypoint after Red Bluff. The modified route is now the same as your clearance. Execute the modification. The waypoints below Oakland in the list move up the same as before. The delete key removes only one waypoint at a time and causes a route discontinuity. If more than one waypoint must be removed, there is an easier procedure. To obey this clearance, you could delete Red Bluff and Oakland using the delete key. A better way is to bypass these waypoints by moving Avenal up in the waypoint sequence. Move Avenal up the list and put it after Rogue Valley. Notice that if you bypass a waypoint and do not use the delete key, you avoid a route discontinuity. Now execute the modification. Red Bluff and Oakland are bypassed and removed from the route. The waypoints below Avenal move up. To obey this clearance, put in CATSO after Rogue Valley. At times, your clearance may include a geographic location that is not in the FMC database. When this occurs, the message "Not in Database" is shown. Clear the scratchpad message and clear CATSO. Waypoints not in the FMC database can be created by reference to other FMC waypoints. Three types of waypoints can be created by a reference to another waypoint. The first is the place-bearing distance waypoint. The created waypoint's location is calculated from the location or place, a bearing from the place, and a distance along the bearing. This is the format you type into the scratch pad to create the new waypoint. The new waypoint is made by the Lakeview 227-degree bearing, 88 nautical mile fix. The second waypoint type is the place bearing waypoint. This created waypoint uses two reference waypoints and the bearing from each waypoint. The third waypoint type, the along track waypoint, is discussed in a different part of this lesson. Now let's go back to the example for CATSO. You see from your aeronautical chart that CATSO is located on the 080 radial of the Sacramento VOR at 49 nautical miles. Make a place bearing distance waypoint for CATSO and put the waypoint into the route after Rogue Valley. Use the Sacramento VOR and remember to put a slash between the bearing and distance numbers. Push The FMC creates a 5-character name for the waypoint. It uses the first 3 letters of the reference waypoint, followed by a 2-digit number. The first waypoint created from Sacramento is named SAC-01. The second waypoint created from Sacramento would be named SAC-02. Now, let's use a different procedure to create the same waypoint. Erase the modification. From your chart, you see that CATSO is also defined as the intersection of the Sacramento 080 radial and the Linden 029 radial. Make a place-bearing waypoint for CATSO. Put in the Sacramento VOR and radial, followed by the Linden VOR and radial. Again, remember to use a slash between the 2 place bearings. The FMC identifies this new waypoint the same as the place bearing distance waypoint. The FMC always uses the first identifier put in to identify the waypoint. In this example, if Linden was put in first, then the waypoint is named LIN-01. Erase the modification. Now let's discuss the along track waypoint. This type of waypoint is different because the reference waypoint must be part of the current active route. For along track waypoints, first put the reference waypoint into the scratch pad. You can line select it down or type it in directly. Then add a slash and the distance from the reference waypoint. For along track waypoints put in before the reference waypoint, place a minus sign in front of the distance. Always put in an along track waypoint on the same line as the reference waypoint. The minus sign or no sign tells the FMC where to sequence the new waypoint. Now put in this along track waypoint. Earlier, you put in new waypoints and made a route discontinuity. But since along-track waypoints are part of the existing flight plan, a discontinuity is not made. Execute the modification. At times, the only waypoints available are specified by latitude and longitude. To make this waypoint, the latitude and longitude is put into the scratch pad. It can then be sequenced into the route the same as other waypoints. To demonstrate this, let's connect this route discontinuity. Put the latitude and longitude for Oakland into the correct line. For latitude and longitude waypoints, the FMC uses a 5-character format. The first 3 characters are WPT, followed by a 2-digit sequence number. The FMC does not recognize this latitude and longitude waypoint as Oakland. A route discontinuity shows the same as with other new waypoints. The necessary waypoint after Oakland is Avenal. Connect the discontinuity. Execute the modification. ATC has instructed you to fly direct to Lakeview. To make a course direct to Lakeview, put LKV into the active waypoint line. The FMC computed direct course to Lakeview shows above LKV. Now connect the route discontinuity. Execute the modification. Now let's go back to your initial route and look at a different situation. ATC has instructed you to fly direct to Lakeview. The weather is bad and you want a different course to Lakeview. ATC has now given you a different course to Lakeview that you must intercept. To obey this clearance, you turn to a heading of 120. Next, put Lakeview into the active waypoint line as before, as if going direct to Lakeview. The FMC computed direct course is shown above Lakeview as before. You must change this course to agree with the clearance before you execute the modification. The FMC lets you put in a different intercept course to the active waypoint. Your clearance refers to the 350-degree radial of Lakeview. The reciprocal of the radial is a 170-degree intercept course to Lakeview. Put in the new intercept course into the intercept course line. The intercept course now shows above Lakeview and on the intercept course line. Now connect the discontinuity. Execute the modification. Now let's look at another example. This time you will intercept a course to a waypoint that is already part of your route. Obey this clearance by moving Red Bluff into the active waypoint line. Any waypoint entered into the active waypoint line creates a direct course to that waypoint. This time the intercept course line is not empty. The FMC has preloaded a default course intercept. The FMC default intercept course is the original course to that waypoint. The preloaded default is displayed in small font. You can select this default course by pushing the line select key, or you can enter a new course intercept as in the last example. To obey this clearance, you need to fly direct to Red Bluff. Take the necessary action. Usually, in-flight modifications to the route are made on the route legs pages, but the route pages can be used for some in-flight modifications. Select the route page. To make modification to the route, go to the next page. On the route page, route segments can be added and bypassed, but cannot be deleted. To add this route segment, put Lakeview on top of Avenal in the first two line. The FMC thinks the route segment is direct. If the clearance includes an airway, it must be manually put in here. Now put Red Bluff into the line after Lakeview. Execute the modification. Now let's look at a modification that is done best on the route page. Here is a clearance for two new airways to be added to the route. To begin, change the endpoint of J1 from Avenal to Red Bluff. With this clearance, Red Bluff is the necessary waypoint after Rogue Valley. Put Red Bluff on the line after Rogue Valley. Now a route discontinuity shows. Complete the clearance instructions to connect the discontinuity. Execute the modification. The new clearance is put in. Let's try one more. With this clearance, Crescent City is the necessary waypoint after Rogue Valley. Put Crescent City on the line after Rogue Valley. Complete the clearance instructions to connect the discontinuity. Execute the modification. The route modifications are complete. Use this clearance and create a place-bearing distance waypoint. Make the new waypoint the active waypoint. Enter the data. Now there is a route discontinuity. Complete the clearance instructions to connect the discontinuity. Execute the modification. The new clearance is put in. Let's try one more. Use this clearance and create a place-bearing distance waypoint. Make the new waypoint the active waypoint. Again, there is a route discontinuity. Complete the clearance instructions to connect the discontinuity. Execute the modification. The place-bearing distance route modifications are complete. Use this clearance and create an along-track waypoint. Execute the modification. Create a different along-track waypoint. Execute the modification. This clearance and create an intercept course 2 waypoint. Put in the intercept course to the new waypoint. Now there is a route discontinuity. Complete the clearance instructions to connect the discontinuity. Execute the modification. This completes the creation of an intercept course 2 waypoint route modification. Use this clearance and create an intercept course 2 waypoint. Put in the intercept course to the new waypoint. Now there is a route discontinuity. Complete the clearance instructions to connect the discontinuity. Execute the modification. This completes the creation of an intercept course 2 waypoint route modification.
In this lesson, some of the significant performance information provided by the flight management computer will be discussed. This will include the cost index, ECON speed, altitude capability, optimum altitude, and the location of performance data in the event of total FMC failure. A cost index must be input every time you initialize the FMC. The FMC will use this cost index to compute the most economical climb, cruise, and descent speeds for the scheduled flight when operating in economy mode. The factors affecting the total cost of each flight must first be determined for an airline to calculate the cost index. The factors which affect the cost of a flight can be segmented into time-related costs and fuel costs. Time-related costs are any costs which will be reduced by reducing the flight time. This reduction in flight time is accomplished by flying faster climb, cruise, and descent speeds. Simply put, the faster you fly, the lower the time-related costs. For most airlines, portions of the maintenance costs are time-related. For some airlines, flight crew and cabin crew costs are also time-related. The chosen flight speeds will also affect the fuel costs. For each flight, there is a specified speed which will minimize the trip fuel and therefore minimize the fuel costs. This speed is determined by aerodynamics and affected by the engine characteristics of the airplane. The goal for an airline is to minimize the total cost of the flight. The total cost would be determined by adding the cost of fuel plus the cost of time. The speed which results in the lowest total cost is the most economical speed for the flight. This speed is called ECON speed. Cost index is simply the parameter entered into the FMC so it can calculate the ECON speed for climb, cruise, and descent. If your airline has low time-related costs or high fuel costs, a low cost index is used. This will result in a slower ECON speed. If the time-related costs are high or fuel costs very low, a high-cost index would be used. This will result in a faster ECON speed. Only your airline can gather the information necessary to determine the best cost index for your operation. Typically, cost index is supplied as part of the dispatch papers or is set by company policy. This is the ECON climb speed. It is the commanded speed if the economy mode has been selected and there is not a waypoint speed constraint, speed restriction, or transition altitude speed restriction active. This speed will provide the minimum total trip cost based on the cost index entered during FMC initialization. High weight or high cost index will result in a higher ECON climb speed. As the airplane climbs to a higher altitude, the climb is flown at a constant Mach number. The FMC will select the ECON cruise Mach number. This eliminates acceleration or deceleration in the transition from climb to cruise. Once attaining altitude, the FMC will fly the ECON cruise speed. The ECON cruise speed is a function of cost index, gross weight, altitude, and actual winds. This speed will change during the flight as fuel burns, the wind changes, or if a different altitude is selected. This speed can vary from a low of the maximum range cruise speed, MRC, at a cost index of 0 to the VNAV limit or cruise thrust speed at a high cost index. Since MRC is the maximum range cruise speed, flying this speed results in the minimum trip fuel and therefore the maximum range. This occurs at the speed where the fuel mileage is the greatest. Another speed you may be familiar with is LRC, the long-range cruise speed. This speed is defined as the Mach number where the fuel mileage is 99% of the maximum. Flying at LRC results in a 10 to 25 knot increase in ground speed for about 1% increase in trip fuel. On the 737-800 airplane, LRC is approximately a Mach number of 77 when cruising near optimum altitude. For example, increasing the speed from 77 to 785, about 10 knots, will increase the trip fuel by about 4 to 5% at normal cruise conditions. At high cost indexes, the airplane's speed may be limited by the VNAV speed limit or the cruise thrust limit. The VNAV speed limit is VMO minus 5 knots. The cruise thrust limit is the speed where the thrust required for level flight equals the maximum cruise thrust available. As temperature increases, the cruise thrust limited Mach number will decrease. After the top of descent, the vertical descent path necessary to meet the first altitude constraint on the legs page at idle thrust results in the descent speed. The target speed is displayed for planning purposes only. As the airplane descends, the highlighted speed will change from the target Mach number to the target IAS. This crossover occurs when the IAS exceeds the target Mach number as the result of the change in altitude. The target IAS is a function of the cost index only. Another performance function of the FMC is to compute the optimum and maximum altitude for the airplane. During normal operations, when the FMC is operating in ECON mode, the optimum altitude displayed is the most economic altitude for the total trip cost. Therefore, this optimum altitude is a function of cost index and airplane weight. If the airplane is operating in a speed control mode, such as at a constant Mach number or at LRC, this optimum altitude is the altitude which will result in the minimum trip fuel. As the optimum altitude increases with decreasing fuel on board, a continuously climbing cruise would be the most cost-effective. But as we all know, ATC will not allow this. In place of a climbing cruise for cost efficiency, choose an initial cruise altitude above the initial optimum for the flight. Remain at this cruise altitude until the optimum altitude has increased above your current altitude sufficiently, then commence a step climb to the highest optimum altitude for the flight. The FMC provides data for crew evaluation for a manually entered step climb altitude on the cruise page of the CDU. This data includes the predicted cost savings or penalty associated with the step climb to the crew-entered altitude and the first possible step climb point based on gross weight. The optimum altitude based on the current gross weight is continuously displayed. The ideal flight path will always keep the airplane within 2,000 feet of the optimum altitude to maximize efficiency. The FMC also displays the maximum possible altitude for crew reference at the current target speed. The maximum altitude is the more limiting of the thrust limited altitude, the maneuver margin limited altitude, or the maximum operating altitude. The thrust limited altitude is the highest altitude the airplane can maintain at the maximum cruise thrust rating or climb to at the maximum climb thrust rating. It is dependent on OAT. This calculation of thrust limited altitude is based on residual rate of climb of 100 feet per minute for cruise and 300 feet per minute for the climb phase of flight. This residual climb rates can be altered on the ground only through an FMC maintenance page. In general, the thrust limited altitude as a function of an outside air temperature will be at least 2,000 feet above the optimum altitude where the temperature is ISA plus 15 degrees Celsius. As previously stated, the maximum altitude is also limited by the maneuver margin limited altitude. The maneuver margin limited altitude is determined by computing the G margin to initial buffet at the selected altitude and speed. This computed margin is then compared to the airline selected minimum G margin. The default for the airline selected maneuver margin is 1.3 Gs. If the FMC computes a margin to initial buffet at the selected altitude and speed that is smaller than the airline selected margin, the selected altitude will not be allowed. A 1.2 G margin is the same as a steady 34-degree bank turn. A 1.3 G margin is the same as a steady 39-degree bank turn. If an engine failure occurs in flight, the Engine Out cruise page can be accessed by selecting the Engine Out prompt on the cruise page. This page displays non-executable advisory data only, and the Execute key remains extinguished. The FMC computed maximum altitude for single engine operation is displayed and is based on a company-specified rate of climb at maximum continuous thrust with one engine inoperative. The default climb rate is 100 feet per minute. If terrain clearance is a potential problem, the engine-out drift-down speed should be flown. The dispatch requirements for terrain clearance are based on this speed. A faster drift-down speed will steepen the descent path and result in a lower level-off altitude. To be a legal dispatch, a net drift-down profile must be able to clear all terrain and obstacles by at least 2,000 feet within 5 statute miles to either side of the flight track. After drift-down, the net profile must result in a level-off altitude that provides at least 1,000 feet of obstacle and terrain clearance. The FAA requires that a net engine inoperative flight path be able to meet all obstacle and terrain clearance requirements. This net flight path is 1.1% of the drift-down gradient lower than the actual drift-down profile. The FMC will provide you with this advisory engine-out speed and predicted maximum altitude of the engine-out cruise page. If an engine failure has been preceded by an FMC failure, the pilot can get the same data from pages in the Performance in-Flight section of the Airplane Operations Manual. On the 737 airplane, the FMC is not required for dispatch. If the FMC performance functions are lost during flight, the pilot can revert to using the performance data in the Performance in-Flight section of the Boeing Operations Manual. This section contains the performance information normally supplied by the FMC. This includes things like engine thrust setting information, cruise data, altitude capability, landing reference speeds, and so on. This performance section also includes landing performance data such as slippery runway, landing distance, non-normal configuration landing distance, and brake cooling. The charts in this Performance in-Flight section are tabular. The chart is used by entering with the known airplane conditions and reading the desired information. On some charts, the desired information is read at a reference condition and then must be adjusted for conditions that are off reference, as in this example. One last comment on the FMC provided performance. The takeoff reference page provides FMC the calculated values for V1, VR, and V2. These speeds are just like the speeds you are used to seeing in the Quick Reference Handbook. They are valid for a standard balanced field length takeoff weight. The FMC determined V speeds do not include clearway or stopway in the calculations. If the takeoff is being conducted on a slippery or contaminated runway, the FMC provided V1 speed is not valid. If improved climb techniques are used, all three speeds, V1, VR, and V2, must be adjusted. In all these special cases, the flight crew must get the takeoff speeds from dispatch.
Each CDU is the backup for the other CDU. If a CDU is blank or does not respond to entries, then it has failed. In this example, the captain's CDU has failed and the first officer's CDU is normal. The FMCs are the primary components of the flight management system. They are very reliable and do not usually fail. If the FMCs do fail, some automatic flight functions and displays will not operate. The indications of FMC failure include the illumination of the FMC alert lights on each pilot's forward panel. The CDU changes to the menu page and the FMC prompt is gone. There is no VNAV or LNAV available if both FMCs fail. The map display is not available. Use conventional methods for navigation. Let's look at other failures associated with the FMC. If power to the FMCs are temporarily stopped, flight plan data might be erased. If power to the FMCs have stopped for less than 10 seconds, then normal operation continues when power is available again. No data is erased whether the airplane is in the air or on the ground. If power to the FMCs have stopped for more than 10 seconds while on the ground, then all flight plan data is erased from the FMC. The data must be put in again when power is available again. If power to the FMCs have stopped for more than 10 seconds while in the air, then the FMC internal battery holds the flight plan data in memory for an extended period of time. After power is available again, the FMC does not know how long the power has been off and is not sure where to go next. The FMC scratchpad message, "Select active waypoint leg," is shown. You must put in the next waypoint and execute to continue normal operations. There are many different systems that input data into the FMC. The removal of one of these items decreases the performance of the FMC. Let's look at fuel quantity input failure. If fuel quantity data is not available, the FMC uses the last known quantity for subsequent performance data. VNAV operates correctly. The message "Verify gross weight in fuel" shows in the scratchpad, and the fuel line on the PERF INIT page changes to dashes. Clear the scratchpad. Put in the estimate of fuel weight. Execute the change. The word "manual" by the fuel weight shows that fuel quantity input is inoperative, and you put in the data. Because fuel is burned, the FMC estimates become less accurate. The message "Verify gross weight and fuel" shows in the scratchpad after 30 minutes to remind you to put in new fuel weight. This makes FMC gross weight data accurate. The FMC supplies outputs for VNAV and LNAV guidance. The VNAV guidance is calculated for 2 engines running. For performance data with an engine out, select the engine out prompt. One engine performance is different between the left and right engines because of bleed air configurations. For this example, select the left engine out prompt. The FMC now shows engine out performance data with the left engine out. A maximum altitude for engine out operation is shown here. The target speed changes to the minimum drag speed. The maximum continuous N1 is shown here. You cannot execute the change. Examine the engine out data. After you look at the engine out data, erase the modification. Engine number 2 is shut down. Use the FMC Engine Out function.